Sometimes. Like this camera.
Okay. Yes, I see. I'll try. I am afraid it won't work all the time, but I'll try to look at the camera from time to time.
As this, what you say that was offline.
I understand.
Online, so I think it would be better if you introduce
myself.
yourself.
Okay.
So
all right.
It will be okay.
I'm going to start from the front camera and then switch to the PowerPoint slide in a few seconds. So you don't need to say it on the microphone.
Okay. Okay. I see. All right.
Keep your mobiles off.
We will coordinate with this mic and speakers. Okay.
All right. Okay.
Once your picture is up, we will start.
So I'm starting now.
Okay. Good morning. My name is Lukas Palatinus. I come from the Institute of Physics of the Czech Academy of Science. And the first lecture from the series of lectures within this Gyan workshop is called Crystallography Refresher, and it is meant to set certain basis of the basic knowledge of crystallography that is needed to successfully follow this workshop on advanced topics in structure solution of inorganic crystal structure. So let's start with the very basic definitions. What is a crystal and what is a crystal structure? So the traditional definition is that a crystal is a three-dimensionally periodic arrangement of atoms, ions, or molecules. This is a very useful, very well functional definition, but it doesn't cover certain less usual types of crystals like modulated crystals or in general periodic structures, and therefore IUCR adopted a more general definition some 20 years ago, which states that a crystal is a solid that gives essentially discrete diffraction pattern. So as soon as you get a diffraction pattern that is discrete or essentially discrete, you can say you have a crystal. But for this lecture and for most of the workshop, we will work with the only 3D periodic crystals, and for them the old standard or traditional definition is valid. So it's a three-dimensional arrangement of atoms, ions, or molecules in a material. So as such, every crystal structure can be described using the mathematical concept of a lattice. So in the first picture, what you see is sort of an ideal or schematic crystal structure, which is periodic in 3 dimensions, and you can find equivalent points in that structure. In this case, the equivalent points were chosen to be here between these blue atoms, and each of these equivalent points is marked in this picture with black circle, and it is a selected lattice point. And you can see that all these points have the same surrounding, and if you connect these points with lines, you obtain a regular lattice. And then you can actually say that the crystal structure is obtained by taking the lattice, so the lattice of black points, and decorating each lattice point with the basis, which is the structural motif. The lattice can be described with the unit cell. So here you see the lattice. This is the this is a lattice of black points, and the green rectangles, or in 3D it would be parallel pipettes. These show different ways of selecting a unit cell in the lattice. So a unit cell can be selected in many ways, in infinite number of ways, but it has to be a parallel pipette, and it has to fulfill certain conditions. The first condition is that all lattice points must be located in the corners of the unit cell, except for the centered unit cells, for which we to which we come later. But the key rules are written here. So, or in other words, out of the infinite number of unit cells that you can choose, there is always one which is so-called conventional. There are conventions that allow you to choose the best unit cell, and these are the rules for the unit cell. So first, the composition inside the unit cell must be the same as the composition of the whole structure. That's true for all unit cells. But then we choose unit cells with maximum symmetry. So if there is a mirror plane in the structure, there should be a mirror plane also in the unit cell shape. There should be minimum volume and maximum possible number of right angles, which is related to the maximum symmetry. So using these rules, we obtain a conventional unit cell for every lattice. When characterizing the structure in using the unit cell concept, or using the lattice concept, we face or meet with various types of coordinates or say objects or mathematical concepts. And so it's useful to review them now. The first is the position of atoms. So what we typically describe the positions of atoms using fractional coordinates. That means that the position of atoms is described as a relative position within the unit cell. So for example, this atom has fractional coordinates of 0.72, 0.81, and the third direction, the third dimension would be 0. So that means that we go 0.72 times the basis vector A, so the first basis vector of the unit cell. Then we move 0.81 times the basis vector B, and then for the third coordinate, if there was a third coordinate, it would go out of the plane of the screen. So these fractional coordinates are related to the basis vectors of the unit cell, so the defining vectors of the unit cell. A second concept that is frequently encountered is a direction. So direction in direct space, so in the space of crystal structure. Here in the second picture, you can see this green line with an arrow at the end, and that defines certain direction in the crystal structure. And again, the directions are expressed as linear combinations of the basis vectors. So they are expressed in the crystallographic coordinates. So this direction is obtained by moving 1 times along A and 2 B. So the indices of the direction is 1, 2, 0. Just the coordinates in the basis of the crystal lattice. Just note that the directions in direct space are enclosed in square brackets. There are conventions about what different brackets mean, and they should not be mixed up, because if you use round brackets or parentheses, that means something else than square brackets and then curly or angle brackets. So directions in direct space are enclosed in square brackets. Another concept that frequently occurs is the concept of lattice planes. So for example, you can connect any 2 points in the crystal lattice, or any 3 points in 3 directions, and you can draw or imagine a plane coming through these 3 points. And then these planes are also denoted by indices, but the calculation of these indices is somewhat more involved or complicated than the calculation of indices for the directions. So here in the lattice, we have to see how many lattice vectors are intercepted by the lattice plane. So in this case, the intercept of this green line along A is 1, and the intercept along B is 2. Then we have to take the reciprocal of that, so we get 1 over 1 is 1, and 1 over 2 is 1/2. So we get indices 1, 1/2, 0. So we again ignore the third dimension because we are just in the plane of the drawing. So we have 1, 1/2, 0, and then we need to multiply these numbers with a suitable integer to get the smallest co-prime integers, or the co-prime integers. So in this case, 1, 1/2, 2 needs to be multiplied by 2 to get 2, 1, 0. And this is the index of this plane. You see the index is enclosed in round brackets. We'll see later that the concept of indices of planes in direct space is closely related with the concept of points in reciprocal space. That is a key concept in crystallography due to the physics of the diffraction. So we will come to this later. But if you want to stick to the description in direct space, then the procedure that I just described is the one you need to obtain the indices of the planes. So you count the intercepts of the lattice vectors, you take the reciprocals, and then you transform to the nearest integers, or to co-prime integers. The key concept in the description of crystal structures is the symmetry. It is key concept for, well, there would be probably many reasons, but the two most important reasons is, first, the properties of the crystal depend on the symmetry, the optical properties, whatever hardness, even conductivity. And the second important concept or fact is that when you describe the crystal structure, you need to know the symmetry. Otherwise, the structure description would not work. You would describe two atoms as independent, although they are not independent, they are related by symmetry. So you need to know the symmetry properly if you want to describe the crystal structure properly. There are different types of symmetries, and the basic symmetry is the symmetry of macroscopic properties like crystal shape or the optical properties. And these symmetries, the macroscopic symmetries, are described by so-called point group symmetry. These are symmetries that keep at least one point invariant, so they do not contain translations. And in crystallography, there are actually only 2 times 5 types of symmetry elements possible in point group symmetry. These are the rotation axis, 1, which is a trivial no symmetry identity, 2, 3, 4, and 6. The 5-fold symmetry is not possible in periodic crystals because you can't tile the plane without gaps with pentagons or with any shape with 5-fold symmetry. So 5-fold symmetry is not possible. So, and these 5 possible rotations can be combined with inversion around the center of the coordinate system. So you may take, for example, the 2-fold axis, so that's a rotation by 180 degrees, and then you may apply inversion across the origin of the coordinate system, and you obtain, like in this picture, this point. So this is denoted as 2 bar. It's rotation combined with inversion. And you see that in this case, this is actually the same as taking a mirror perpendicular to the rotation axis. So 2 bar is usually not denoted 2 bar, it's denoted M as for mirror. The 3 bar is just the same concept, so you rotate 120 degrees, like a 3-fold rotation, and apply inversion center, when in fact A 3-bar axis is obtained as a combination of a normal 3-fold axis and inversion center. 4-bar, again the same concept. So you rotate 90 degrees, you invert, and if you imagine doing this 4 times, you obtain something like a elongated or squeezed tetrahedron. So not regular tetrahedron, but deformed tetrahedron. So these are the possible symmetry elements that you can encounter in point groups, in crystallographic point groups. And based on the different symmetries, there are classifications of symmetries to crystal systems, to lava groups, and to point groups. And we will go through this concept. So the most coarse classification of crystals is into 7 crystal systems. And the crystal systems are, roughly speaking, the classification by the highest possible symmetry. So you see, you know there are 7 crystal systems. Triclinic crystal system may have no symmetry, or it has no rotation or rotary inversion axis. Then the monoclinic system has just one important symmetry direction. Orthorhombic has 3 perpendicular symmetry directions, so either 3 mirror planes or 2-fold axis or any combination of that. Then we come to the higher symmetries. Tetragonal has 1 4-fold axis, hexagonal has 1 6-fold axis, and trigonal has 1 3-fold axis, and the highest system, the highest symmetry is cubic, which has 4 different 3-fold axes present in the system. So this, what I said, is actually the definition of the crystal system, but this is not how you recognize it first, because usually the first information we have about the crystal structure is not the symmetry, but the unit cell dimensions, so the unit cell parameters. So therefore you see in this central column, you see the properties of the unit cell parameters for the different crystal systems. For example, you can see that for orthorhombic crystal system, you have A different from B, different from C, and all 3 angles between the 3 vectors are 90 degrees. And each crystal system has a different set of constraints on the lattice parameters. However, this node here is important. This unequal sign means may not be equal. So if A equals B, for example in orthorhombic, it doesn't mean that the structure cannot be orthorhombic and must be tetragonal. So if it's tetragonal, then A equals B always. But if A equals B, that does not imply necessarily that the structure is tetragonal. Okay? You may have an orthorhombic structure which has, by coincidence or by crystal chemical rules, A equals or almost equal B. So these are properties of the crystal systems, but they are not defining the crystal system. It's the symmetry that defines the crystal system. That's important to keep in mind when you do the practical crystal structure determination. All right. So then, when we have the point group symmetry operators, there are exactly 32 ways to combine different point group operators into point groups. So there is a finite way how you can combine 2-fold axis, 3-fold axis, 6-fold axis, and mirror planes and other roto-inversion elements into symmetry groups. And here you see the list of them. So again, for each crystal system, you have certain number of possible point groups. They are listed here using their Hermann-Moggen symbol. So they include the symbol of the highest symmetry element in each of the characteristic directions. And you see that the characteristic directions are different for every crystal system. So for triclinic crystal system, there is no characteristic direction because there is no rotation axis. For monoclinic, there is just one symmetry direction. So that's the characteristic direction, obviously, which is by convention typically 0, 1, 0. So the monoclinic direction is set to be along B, although you can find also conventions where it is set along C. So it's just a matter of convention. Then in orthorhombic, there are 3 perpendicular possible directions with rotation or rotoinversion. So these are the A, B, C directions, and you need to specify the symmetry along each of these directions. So for example, this point group 2, 2, 2 is telling you that there is a twofold axis along A, twofold axis along B, and twofold axis along C. In tetragonal, you may notice that the characteristic directions are different from orthorhombic. It's 0, 0, 1, that is the direction of the tetragonal axis. 1, 0, 0, so that's the A direction. But then 0, 1, 0, that's present in orthorhombic, makes no sense in tetragonal because by symmetry 0, 1, 0 and 1, 0, 0 are the same. They are symmetry equivalent because of the fourfold axis. So 0, 1, 0 is the same as 1, 0, 0. But there is a diagonal direction between A and B, which also may host some symmetry elements. So in tetragonal, the third characteristic direction is 1, 1, 0. And therefore, for example, if we pick the point group symbol 4mm, this is telling us that along 0, 0, 1, there is a fourfold. There is a 4mm. There is a fourfold axis. Along 1, 0, 0, there is a 2-bar. So you remember, mirror is the same as 2-bar rotoinversion. So there is a 2-bar rotoinversion along A, which means a mirror perpendicular to A. And then there is M, so again, 2-bar parallel to 1, 1, 0, which actually means a mirror perpendicular to 1, 1, 0. So this is a little bit tricky. If you see a mirror plane, then it actually means that the mirror plane is perpendicular to the given characteristic direction. But this is just because we are used to the, like mentally used to the concept of mirror, but in fact it's the 2-bar rotoinversion that is parallel to that direction. You can also see the division of the point groups into various classes. So the green ones, sorry, the red ones are those that contain inversion center, and the green ones are enantiomorphic point groups. So these are point groups of crystals that can host chiral molecules or chiral objects. This is most important in organic chemistry and bio-related chemistry, where we often know that we have molecules which do not have their proper inversion center or mirror plane, and then we know that we are limited in symmetry to certain point groups and space groups. The last column is the Lavais group corresponding to these point groups, and the Lavais group is just a point group with inversion center, and that is important for the description of crystals by diffraction, because as we will see later, the diffraction pattern always has an inversion center. So the point group of diffraction pattern is always one of the Lavais groups. So it's a point group which contains inversion center. Okay, so this is the overview of the 3 highest symmetry crystal systems: trigonal, hexagonal, cubic. Again, the idea is the same. There are certain unit cell parameter restrictions. This is the highest symmetry type, and these are the characteristic directions, which are in trigonal it's the C and the A. In hexagonal it's C, A, and then the diagonal between not A and B, because A and B have angle of 120 degrees, and the diagonal between them is actually equivalent by 6-fold axis, but it's the diagonal, let's say that's the direction 30 degrees off the A. That's the third characteristic direction for the hexagonal system. And in cubic, if you imagine the cube, the 3 specific directions are the edge of the cube, the face diagonal, the second is the body diagonal, 1, 1, 1 is the body diagonal, and the third is the face diagonal of the cube. So these are the three special directions in cubic. And again, you see the list of possible point groups and their separation into the Lie groups. I have to apologize, PowerPoint somewhat strangely renders some of the symbols. So here you can see a little dot above the 3. That should be actually bar. So this is actually a 3 bar. This is a 6 bar, 6 bar 2m. It's unfortunate, but I didn't find a way to render it better. I hope you can see it at least a little bit. So that was 32 point groups, but crystal structures, they are, in ideal case, they are infinite objects. You take the unit cell and you repeat it periodically in all 3 directions. So you need to introduce also translation. So crystal structures do not have only point group symmetry, they have so-called space group symmetry. And the space group symmetry differs from point group symmetries by allowing also for translations. So in other words, space group symmetries are symmetries of infinite objects. So in that case, we can combine our well-known now rotations and roto-inversions with possible translations, and we obtain new symmetry elements. If you combine the translation with just the trivial symmetries, so pure translation, you obtain a lattice, and you can find that there are 14 different types of lattices that differ by their symmetry. And these are so-called Bravais lattices. We'll come to that on the next slide. Then if you combine translations with glide planes, translations with the mirror plane, you obtain so-called glide planes. So these are symmetry operations where you combine mirroring on the plane and shifting along certain direction. And then if you combine translations with rotation axis, so 2, 3, 4, or 6, you obtain so-called screw axes. And then if you look for all possible combinations of all these symmetry elements together, you arrive to the conclusion that there are 230 possible combinations of symmetry elements of infinite objects, and these are the 230 space groups. So for the lattice types, again, every crystal system corresponds to a certain number of lattice types, and these lattice types differ not by so within each crystal system, the unit cell has the same overall shape or symmetry, but it may have additional so-called centering points. So you may have an equivalent point inside the unit cell. For example, in this case, the monoclinic, this unit cell is primitive, so there is a little black dot only in the corners of the unit cell, but in this cell there is additional point just in the center of the base of the unit cell. So this means that if you have an atom in certain relation to this, to the central, to this point, there will be an equivalent position here, but also in the center of the base of the unit cell. And this is called so-called C-centered unit cell or C-centered lattice. And C is because this plane where the centering appears is facing the C direction. And there are various types of these centerings. It's the C centering. You may have the A and B centering, which is again a centering in the face facing the A and B direction. There is also an I centering, which you can see here. I comes actually from the German word innenzentriert, which means centered inside. So there is one equivalent point in the center of the unit cell. And the last two possibilities, but the last one that I want to mention is the F-centered, again from German flächenzentriert, which means face-centered. So then the centering points are in the centers of all faces of the unit cell. And there is also a so-called R centering, which is a centering describing certain trigonal types, but I will leave it aside for the moment. You may ask why there are not all types of centerings in all crystal systems. So why isn't here a eye-centered monoclinic listed or face-centered monoclinic? The answer is you can construct such cells, but you can then show that you, by equivalent transformations, you can transform them into another one. So for example, here is just an example why there is no F-centered tetragonal cell, because if you draw such an F-centered tetragonal cell, you may transform it to a smaller cell which will be I-centered. So tetragonal F-centered is equivalent to tetragonal I-centered, and therefore, again, by convention, only one of them is considered independent and standard. So there is, for example, also no C-centered cubic, because the symmetry of the cubic structure is such that if you have a C-centering, you must have by symmetry also A-centering and B-centering, and the result is an F-centered cubic lattice. So altogether 14 different types. The space groups are in crystallography described by the so-called Hermann-Mogen symbol that combines the symbol for the Bravais class with the symbol of the main or characteristic symmetry elements or operations along each of the characteristic directions of the crystal system. So we need to know the characteristic directions of each crystal system, and then we can say what are the elements in that particular space group along these directions. So for example, the PBCA is an orthorhombic crystal system. I will tell you soon how do I know that. Well, you can read it in this table. So the first letter describes the Bravais class. P means primitive, so there are no centering points. And then I know there is a B glide perpendicular to the A direction. There's a C glide perpendicular to B direction and A glide perpendicular to C direction. B glide means that the mirroring is combined with a shift of 1/2 along the B direction. So I take a mirror and I shift by 1/2 along B. So that's a B glide. C glide equivalently means shift along C direction. Excuse me. And A means shift along A direction. What crystal system is this? You can find from this table. So again, if you see there are 3 different mirror planes or twofold axes and no higher symmetry, then you know you are in orthorhombic. If there is just one position, it's monoclinic. If it's only one or one bar, then it's triclinic. And for the higher symmetries, you determine it from the highest visible rotation axis. So if there is 4-fold, 6-fold, or 3-fold, on the first position, it's tetragonal, hexagonal, trigonal. And if there is a 3-fold on the second place in the symbol, that means it's a 3-fold along the body diagonal of the cubic system. So this corresponds to this case 3 perpendicular mirror planes, no higher symmetry, so this is orthorhombic. So if we want to find the point group from the space group, which is important because we need to relate the symmetry of the crystal system with the symmetry of the diffraction pattern, again we'll come to this a bit later, then the recipe to get from the space group to the point group is very simple. You discard the symbol for the Bravais lattice and you replace all the letters which stand for glide planes or mirror planes, you replace it with M. So from P, B, C, A, you obtain the point group M, M, M. Unfortunately, the next step to Lavais group is not so simple because there is no algorithm, no simple recipe to recognize if there is an inversion center present in the point group or not. So the easiest way is to take the table of point groups and Lavec groups and compare and see what is the corresponding Lavec group for the point group. After a little while, you get the experience and you see it very quickly yourself. You don't need tables anymore. And then going to the crystal system from the point group or Lavec group is through this table. So you just check the number and order of the highest symmetry elements, and that allows you to recognize the crystal system. Another example, P M3 bar M. Again, this is a very simple example. We discard the Bravais lattice symbol. There are only M's, no other letters. And again, looking at the table, you would see that this is a point group with inversion center, so that gives you also the Lavec group. And because there is 3 on second place, this is a cubic crystal system. And the last example, P432. Again, the point group is 432, but then the corresponding Lavec group looks very different. It's M3 bar M. And obviously, the same Lavec group means also the same crystal system. So this step, the first step is simple. The second step is less simple. Of course, there is a way to derive it without tables, but the simplest way for the beginner is to have a table at hand. And then going from Lavec group or point group to crystal system, that's again quite easy using the knowledge of the highest symmetry. So a little summary on symmetry. You might notice that symmetry is really a complicated, long topic, and we could easily hold a full 1-week workshop only on symmetry. So this was really just very brief overview. So this is a little summary. There are crystal systems which have certain typical highest symmetry elements, certain typical characteristic direction, and there is a number of space groups belonging to each crystal system. Here you see an example or examples of different space groups, their corresponding point groups, and their corresponding Lavec groups. So I repeat, space group is the symmetry of the crystal structure, an infinite object. Point group is the macroscopic symmetry, so that's the symmetry of the crystal shape for an ideal crystal, and possibly symmetry of physical properties. And Lavec group is a point group with added inversion center, and this is the symmetry of the diffraction pattern that we obtain from the crystal. Interestingly, the number of space groups in different crystal systems is very unevenly distributed. So there are only 2 space groups in triclinic, but there are 68 different space groups for tetragonal. And even more interestingly, the distribution of space groups in actual crystal structures is also very uneven, and it differs a lot on depending on the materials that you study. So here you see an example of space group frequency in the CSD, so crystal structure database, which combines organic or contains organic and organometallic materials. And there you see that more than 1/3 of all structures deposited in this database have the space group P21/C. Sometimes you can hear refer to this space group as God's favorite space group, because really there are people who made their whole career on using only or doing only structures in P21/C. You see, really one of 3 structures, if you work in organic, organometallic, will be P21/C. There is also a large number of non-central symmetric space groups. P21, 2121 is almost 10%. In ICSD, the distribution is quite different, although P21/C is also quite popular. So, sorry, ICSD is Inorganic Crystal Structure Database, so inorganic structures. But you see that the distribution is much more even. The most frequent space group, PNMA, is only 7%, or a bit more than 7%. And you do not find any non-central symmetric space group in the list of the most frequent ones. So far I spoke about crystal structures as objects without considering anything about how we determine them. I described their symmetry, I described the lattices, but I didn't speak about the way to figure out what these things are. And of course, you know that the means of learning or determining crystal structures is diffraction. X-ray diffraction, neutron diffraction, or electron diffraction. Well, nowadays, with modern microscopes, you can do actually direct imaging of structures. So now we can do really microscopy, but the purpose of this workshop is the structure determination from diffraction data. So we'll speak about diffraction. And to understand the diffraction, we need to introduce the concept of reciprocal lattice and reciprocal space. The derivation of the reciprocal lattice and the derivation of why the diffraction follows the concept of reciprocal lattice is very interesting, very nice, very entertaining exercise, but we do not have time to do that entirely. So I will just briefly outline the concept of reciprocal lattice and then briefly explain why is this concept useful in understanding of the physics of diffraction. So when deriving the reciprocal lattice, we can start from direct lattice. So this is an example of a crystal lattice. The blue points here are the lattice points in direct space. So this is really crystal lattice, and we have basis vectors A and B. Again, the C would go out of the plane, so we will stay in 2 dimensions for this explanation. Now, to construct the reciprocal lattice, we first realized that you can plot lines and, let's say, or you can construct the lattice planes, which go like this. This is one set of lattice planes, and this is a second set of lattice plane, which go along the A and along the B, and they have certain lattice spacing. This lattice spacing here is not the same length as the length of the B vector, because the B vector does not necessarily have 90 degrees to A, so the lattice spacing has somewhat different length than the length of the B vector. Now, when we have the lattice spacing, we construct a line that is perpendicular to the lattice planes, and on that line we draw a point with distance reciprocal to the lattice spacing. So the shorter this distance here, the longer the distance of the red point from the origin. We do the same for the second set of basic lattice spacing, so the set that goes along A. Again, the D100 so that is the lattice spacing along this direction. We construct a line perpendicular to the lattice spacing, and we place there a point with the distance from the origin 1 over D100. Again, the longer this, the shorter this. Because of this reciprocal relationship, we call the reciprocal space reciprocal space. And with this construction, we obtained 2 points which defined 2 vectors that can be used to construct another lattice. So this is typically denoted with star. So this vector which goes not parallel but in the direction of A is called A star, and the one that's perpendicular to A and goes somewhat in the direction of B is called B star. And using these basis vectors, we can construct a complete new lattice, which is called reciprocal lattice. So you see that the reciprocal lattice is different from direct lattice. The points do not overlap except for the origin, but there is a clearly defined relationship. So if you have the direct lattice, by this mathematical or this geometrical construction, you can construct the reciprocal lattice. And expressed mathematically, these are the equations, the formulas to obtain the reciprocal lattice vectors from the direct vectors. So you take the vector product of the 2 complementary direct vectors, and you divide it by this expression, which actually means the volume of the parallel pipette spanned by A, B, and C, and you obtain the vector A star. So by definition, A star is perpendicular to B, perpendicular to C. B star is perpendicular to C and A, and C star is perpendicular to A and B. And the length of the reciprocal lattice vectors is given by the reciprocal of the corresponding lattice spacings. Continuing on the relationship between direct and reciprocal space, there is, by construction, there is an important relationship between the planes in direct space and directions in reciprocal space. And these are frequently used in crystallography, and they are related to the concept of Bragg's law, which I'm sure you've heard about and you're probably using. And so to understand the Bragg's law concept, we need to introduce this relationship. So we constructed the reciprocal space by considering special set of lattice planes, set that goes like this, so parallel to the basic lattice vectors. But we may, so this is the reciprocal lattice. We may also take another lattice plane, for example, lattice plane going like this. So this is a lattice plane with indices 2, 1, 0, because the intercept along A is 1, intercept along B is 2. So we have 1, 2, then we take the reciprocals, that's 1, 1/2, and multiplying by 2 gives us 2, 1. So the index of this lattice place is 2, 1, 0. And by construction, if you take the lattice plane like this, there is always a point in reciprocal space which is, or the vector in reciprocal space is perpendicular to this lattice plane, and the indices of this point are just the indices of the lattice plane. So you see in reciprocal space this is 2, 1, 0 without brackets. It's just the index of the lattice point, and you see that we can obtain this point by going 2 times along A star plus 1 times along B star. So it's 2, 1, 0, but this time it's not the coordinate of planes or indices of planes in reciprocal space, it's indices of a point. So every point in reciprocal space corresponds to a certain set of lattice planes in direct space. Okay, and finally, what is all this good for? So far it was just a mathematical or geometric exercise. But again, it turns out, and we do not have time to derive this relationship, but it's a very interesting and actually comparably simple thing to derive that this is true. But it turns out that the diffraction follows the geometry of reciprocal space. And the best way to visualize this is the concept of Ewald sphere, which you can see here. So I will describe the Ewald construction, and you'll see how the reciprocal space enters the construction. So in the Ewald construction, the crystal, which is here, the blue object, is placed in the center of a sphere with the diameter of 1 over lambda. So the diameter of the sphere is the reciprocal of the wavelengths of the radiation we are using. And then the S0, so this direction, that's the direction of the incident beam. So the beam comes from here and hits the crystal and then penetrates the crystal and continues in the horizontal direction. The direction S here is one of the possible directions of scattered radiation. So the radiation may be scattered from the crystal in all directions, and we choose one, just one of them, and denote it S. And the vector R star is so-called diffraction vector. That's just the difference S minus S0. And it turns out, or it can be shown, that if you have a crystal, then the diffraction appears only in discrete set of points, so not in all directions. In most directions the diffraction is 0, and the diffraction is non-zero only in certain directions. And these directions can be obtained by placing the reciprocal lattice at the point of intersection of the incident beam with the surface of the Ewald sphere. So this is the origin of the reciprocal lattice. Then you draw the reciprocal lattice derived from the direct lattice. So this is the A and B, and this is the corresponding A star, B star. You draw the lattice, and only if a point of the reciprocal lattice lies on the Ewald sphere, like in this case, only then there is a beam of diffracted radiation going from the crystal to this point. And then if you place a detector somewhere here, you would detect a radiation in the continuation of this point on the detector. So in this picture, there will be actually only one diffracted beam going here, and all the there will be a second beam here because this point here also lies on Ewald sphere. This almost but not quite, and this is also already out of Ewald sphere. So you would have only two diffracted points. And now if you want to change the diffraction, what you need to do is to change the orientation of the reciprocal lattice, and that you can do by changing the orientation of the crystal. So if you rotate the crystal, you rotate the reciprocal lattice because the two are related, and you get a different picture. So in this case, I rotated the crystal slightly counterclockwise. The reciprocal lattice rotates in the same way, and then suddenly this reflection is not in diffraction position anymore, but there is another reflection in diffraction position. So we will get a different diffraction pattern. And this is again one more example with continuing rotation counterclockwise. So if you learn and understand the concept of Ewald sphere, you can really imagine what's going on in the diffraction. All different diffraction techniques, including powder diffraction or a Laue diffraction with wide beam, all can be visualized in one way or another using the concept of Ewald sphere. And I really recommend, if you have not done it yet, I recommend you to study this concept in depth and really understand it, because it really facilitates your understanding or the way of thinking about diffraction. The last thing on this topic is the relationship between the Ewald construction and Bragg's law. Bragg's law is typically the first relationship that is introduced when talking about diffraction on crystal structures. Unfortunately, it's a law that is not as general as the concept of Ewald sphere. So the Bragg's law follows from the Ewald sphere, but not vice versa. So it's really the Ewald sphere and the related mathematical concepts like Laue conditions are more informative. It's better to know that than to focus only on Bragg's law. But you can derive Bragg's law easily from the Ewald sphere construction. This is the picture of the Ewald sphere. I told you that there is always a set of lattice planes perpendicular to a direction in reciprocal space. So for example, perpendicular to this reciprocal vector, there is a set of lattice planes that's shown here, and the d-spacing between them, so the lattice spacing, is just the reciprocal of the length of the vector in reciprocal space. And then if you look at the geometry, you see that the half of the length of the diffraction vector is equal to the length of S times the sine of half the diffraction angle, which is here called theta. So d star half equals length of S, which is 1 over lambda by the construction of Ewald sphere, times sine of theta. And now you can rearrange this relationship, putting 2 to the right and d star to the left and lambda to the right. You get this relationship, and because d star is just the reciprocal of the lattice spacing, you replace d star with d, and you obtain the familiar form of Bragg's law. So Bragg's law follows directly and immediately from the Ewald construction. All right. So that was the geometry. So far, we considered mostly the geometry of the crystal structure, be it the symmetry or the diffraction. We considered only the positions of the spots, and we did not really speak much about the contents of the unit cell, about the structure. And that we will do now. And we'll start with the description, or with the concept of structure factor, which is a way to describe the amplitude and the phase of the wave diffracted from a crystal, point. This is the formula for the structure factor, and the constituents are these. HKL are the indices of the corresponding reciprocal space vector. So coming back to the Ewald sphere, we need to assign the intensity or amplitude, more precisely amplitude and phase for each diffracted beam. When we have a reflection in diffraction condition, there is a beam going from the crystal to that in that direction, and this beam has certain amplitude and certain phase. And we need to describe these two. And that is what the structure factor is telling us. So it is a complex number which has amplitude and phase, and the HKL are the indices of the corresponding point in reciprocal space, and the summation runs over all atoms in the unit cell. Fn is the scattering power of nth atom. So each atom has a different scattering power. Heavy atoms scatter more, light atoms scatter less. And then there is a phase factor that defines how the waves scattered from different atoms interfere with each other. And in this phase factor, we have the scalar product of the diffraction vector HKL with the fractional coordinates of the atom in the unit cell. So xn, yn, zn are the xyz fractional coordinates of the atom in the unit cell, and HKL are the diffraction indices, so the indices of the reciprocal vector. This is the formula that is a complex number, as I said, so it contains amplitude and phase. Unfortunately, in the diffraction experiment, we do not measure this complex number directly. We measure the intensity, which is proportional to the amplitude of the structure factor squared, in certain approximation that is very well valid for X-rays. And therefore, we lose the information about the phase of this complex number. So we do not have direct access to structure factors, we have access only to the structure factor amplitudes. And this is called, known in crystallography as a phase problem. And this is a key problem in crystallography that we need to solve if we want to go from the diffraction to the crystal structure. Anyway, there are many interesting properties that follow from the formula for the structure factor, and one of them, a key basic property, is that the structure factor of two reflections with opposite indices has the same amplitude. This is called or known as Friedel's law, but it's not actually a law because it's violated. It's violated in all cases, so it should be better called Friedel's rule because it's fulfilled to very good accuracy, and for practical purposes we can use it as law, although as I said, it's violated. You can find it very easily by writing the structure factor equation for a reflection HKL, and then if you replace HKL by minus H minus K minus L, so the opposite diffraction vector, there are minus values here, and you realize that you obtain the same formula here as here, except for the minus value here, which means that you get two complex conjugate numbers. So in Argon diagram in the complex plane, this is the structure factor HKL. This is the structure factor minus K minus L minus H minus K minus L, and directions of the arrows are different, but the length of the arrows is the same. And because the intensity is proportional to the square of the amplitudes of the lengths of this arrow, the two amplitudes are the same. Therefore, the reflection pattern always contains a center of symmetry to very high accuracy, even if the structure as such does not have inversion center. The reason why this rule is broken is the resonance scattering. The resonance scattering is an effect where the scattered photons do not have certain phase shift, which is caused by absorption effects, by absorption effects, and then the Friedel's law is not followed, and that's why we are actually able to determine also the absolute structures of non-center symmetric structures, but to very good accuracy, the Friedel's law is present. Just let me check what's the time. Okay. A very important consequence of the structure factor formula and very important property of diffraction are so-called reflection extinction or reflection absences. So in presence of certain features in the structure, certain reflection amplitudes go to zero. There are two types of extinctions or absences. You can hear both words for the same thing. The first one is the trivial, non-systematic, so random case where certain reflection is zero or almost zero just because of the specific arrangement of atoms in the structure. So the scatterings of that atom, of those atoms, cancel, and you get the reflection with a very weak, very small intensity. But that is not telling us much before we know the structure. But more important, more interesting are the systematic extinctions. And these are caused by special lattice centerings, presence of glide planes or screw axes in the structure. Again, there is a very nice way to derive the systematic absences for an arbitrary symmetry element, and it's shown on this slide. I will go briefly through it, but if you do not want to go or to learn this derivation, there is of course an easier or faster way to get to the systematic absences, and that is opening the international tables for crystallography, where you have tabulated systematic absences for each and every space group out of the list of 230 possible space groups. But these tables do not come from from nowhere. They have been derived by people, and the people used the properties of structure factors to derive these formulas. And this, all you need for this is actually these three equations. The first equation gives us the relationship of structure factors between two reflections related by certain symmetry element R. So this R is a matrix that stands for certain point group symmetry element of the structure. So it may be a mirror plane, it can be a rotation axis, and it tells us that if we have one spot in diffraction pattern and associated structure factor with this spot, then the structure factor associated with the spot related by the symmetry, so for example related by a mirror, can be obtained from this structure factor by applying this phase factor, and the phase factor contains the indices and the translation part of the symmetry element tau. So every symmetry element has its rotational part and its translational part. The rotational part may be the rotation axis or the mirror plane, and the translation may be zero, so then it's pure mirror plane or pure rotation. And it may be non-zero, like in this case, it may contain translation along C, so in this case it's 0, 0, 1/2. And that means that after the rotational part, which in this example is a mirror perpendicular to B, so we are changing the B coordinate, and then we apply a shift along C by 1/2. So this is a symmetry operation corresponding to a C glide perpendicular to B. So we have a mirror perpendicular to B, we do the mirroring, and then we shift by 1/2 along C, a C glide. So this R enters here, and the tau enters here in the formula. And this is very general formula that works for all pairs of symmetry-related structure factors. But in specific case, you can have a situation where the reflection indices stay invariant under the operation. So you take a reflection, you apply the symmetry operation, and you stay on the same spot. That is true for all reflections lying on the mirror plane, all reflections lying on a symmetry axis. So in this case, well, we can obtain the conditions for this reflection by solving this equation. This is done here, and the conclusion is that in this particular case of a C glide perpendicular to B, these reflections are those which have the K index equal to 0. So this may be H may be anything, K must be 0, L may be anything. So we get the condition H, 0, L. So these reflections are the special ones that are invariant under the symmetry operation. This equation is valid for this reflection as well, but then we can replace the HR with H, and we get an equation that binds the structure factor with itself. So there is FH on both sides, but still this equation must be valid. There are only two options. Either this phase factor is equal to 1, which means that the scalar product H dot tau is an integer number, and then we get a trivial equation FH equals FH, and that's fulfilled for any structure factor. Or this phase factor is not 1, which is the case, for example, in this particular case when L is an odd number, then the result of this expression is -1. And then we get an equation FH equals minus FH, and this can be fulfilled only in one case, and that is when the structure factor is 0. So we come to the conclusion, and I understand that this was very quick derivation, but you will have these presentations available, so you can go through it slowly later, or we can discuss it if you want. We come to the conclusion that if the L index for these reflections, for the reflections of the type H0L, if the L index is even, then the reflection may be present, but if L index is odd, the reflection must have 0 intensity, so it will be absent. So I know that this may sound complicated, but actually if you study it, you realize that to derive any systematic absence of any symmetry element in any space group, the only thing you need to know are these two equations. That's all. And you can derive everything. That's, I think, quite elegant. All these international tables, or a very large part of that, not all, but very large part of that is contained in these two equations and some background knowledge. Okay, let's have a look at some more geometric examples. Less formulas, more pictures. The first type of systematic extinctions are the lattice type extinction or lattice extinctions that are caused by centering. So a primitive lattice doesn't give you any systematic absences, but if you have I, F, or A, B, C centered lattice, you will see certain type of systematic absences. And here you see how different sections of reciprocal space look for a C-centered lattice. So the C-centered lattice gives you, and again you would derive it using the equations that I just presented, it gives you systematic absences of the type H plus K equals 2n. So the sum of the first two indices must be even to observe the reflection. And if it's odd, then the reflection is absent. So in the HK0 plane, you see that every other reflection in a checkerboard manner is missing. In the HK1 plane, it looks just the same, because the L index does not enter the expression for the systematic absence, so all planes along L look the same. If you look at the H0L plane, you see that every other line along A is missing, and if you look at 0 KL plane, so that's a plane perpendicular to A, then again every other line of reflections is missing. So if you look at the diffraction pattern or at the reconstruction of sections through the diffraction pattern, you can easily recognize that there is a pattern of systematic absences, and the pattern is specific to certain lattice type. This is a little overview of different centerings giving different types of absences. So this is the C that we've seen already. This is F centering, which gives you very sparse diffraction pattern, and you see that here HK0 and HK1 are different because the L index is entering the conditions. And this is the I centering, so the body-centered lattice, which gives this type of pattern where again the HK1 and HK0 are different. Then you have the systematic absences due to the glide planes and screw axis. I will not go through details of that. You have an overview of different glide planes perpendicular to different directions, so different classes of reflections are affected on the reflections that lie on the symmetry element, and this is the list of reflection conditions. The reflection conditions are listed as conditions for presence and not absence. So if you see H equals to N, this is a condition for the reflection to be present in the diffraction pattern, so to be visible. Okay. At the end of this little crystallographic refresher, we added a few slides on a little different topic, and that's not the basic crystallography, but let's say basic crystal chemistry for inorganic structures, because this is something that you need quite a lot when solving and interpreting the structures. Once we get the structure, we need to know if the structure is reasonable or not. We need to know if I see two oxygen atoms which are 1.2 angstroms apart, if that is possible or if it's not possible. And this is validation is nowadays probably the most important part of the structure determination process, because using all the powerful programs that we have now at hand, you always get some structure out of your data, and it's your task to determine if that structure is correct and if it's reasonable. And there are many rules and many ways to check if the structure is correct, and they are quite different for organic and inorganic materials. And because this workshop deals with inorganic structures, we will focus on the validation of inorganic materials, and the basis for the structure description of inorganic materials has been set by Pauling with his famous Pauling's rules. And this is a little overview of these rules. These are not laws, these are rules, and rules are there to be violated. So there is always an exception to a rule, but they give a reasonable starting point, and if you see a deviation from the rule, it's good to double check that it's really a real violation and not just a mistake in the interpretation or mistake in the structure. So just going quickly through the rules, the first one actually tells you that the coordination of cations in an inorganic structure is determined by the cation-anion radius ratio. So the smaller the cation and larger the anion, the smaller the coordination number of the cation. And so you may have, with very small, highly charged cations, you have usually small coordination numbers, and you get coordination polyhedra like tetrahedron. Typically for sulfur 6+, you typically get an SO4 tetrahedron, while large cations like barium or lead may have a large number of coordinating oxygens. Then there is the electrostatic valence rule that essentially tells you that the anions like to have local charge balance. So the number of effective charges on an ion tend to be equal to the charge of that anion. In other words, you will not have a strongly overbonded anion in one place and strongly underbonded anion in another place. Although, all in all, the structure would be charge balanced, but this rule tells you that there is a tendency to have also local charge balance. A rather useful and easily verifiable rule is the third one, and that tells you that the polyhedra in the structure tend to share as little as possible. So mostly the polyhedra will share only corners, less frequently edges, and even less frequently faces. It's possible, of course, there are structures with face sharing polyhedra, but the structure with only corner sharing polyhedra or instances of corner sharing polyhedra are much more frequent. Then, if you have a structure with different cations, some of them highly charged, some of them less highly charged, then there is a tendency for the highly charged cations to be separated as much as possible in the structure. So you will not have two, again, I may use the SO4 as an example, you rarely have two SO4 tetrahedra very close to each other. They tend to be spread in the structure as much as possible, separated by other less charged cations. Because these highly charged cations, they tend to minimize the electrostatic repulsion between them. And the last rule, in my humble opinion, the least useful, but yeah, that's it's also interesting to observe. There is usually a small number of different polyhedra in one structure, and more specifically, one type of atoms tends to have the same polyhedron in the crystal structure. Again, there are exceptions to that, but in general, you'll find that one type of cation typically occupies only one type of polyhedron in the crystal structure. So these are the rules that were derived a long time ago on comparably simple elementary types of inorganic structures, and as you go to more complex instances, there are cases of violation of the rules, but there are very useful concepts derived from these rules, or let's say quantifications of some of these rules. And one of the probably most useful concept that is used in crystal structure validation is the bond valence model. And the bond valence model is a semi-empirical concept that relates the geometry of the structure with the valence of the atoms in the structure. So the bond valence is it's calculating it using this formula where R0 and B are empirically determined constants. So they were determined by looking at a large number of structures with certain pairs of cations and anions, and it allows you to calculate the valence of an atom only from the crystal structure. And we will see it in the examples several times that this can be really used very well for validating the structure. You calculate the bond valence of a cation. You know that this cation should be 1+, for example, it's potassium. You calculate the bond valence and you obtain the value of 5.5. Then you can be sure that this is wrong. If you get a bond valence of 1.3, that's also not 1, but it's not that far off. So there you can think maybe it's okay, probably it's okay, but if you get 3 or 5 or 8, then something's really wrong. So we'll talk about it in the exercises, but I really recommend for inorganic materials to always check the bond valence sum. It allows you to avoid many of avoidable mistakes. There are other values that you can calculate for polyhedra, like the mean fictive ionic radius, or the econ, the effective coordination number. They all tend to express quantitatively some of the Pauling's rules about the coordination polyhedra. A quite useful value is this quadratic elongation that tells you how much the polyhedron is deformed. And all these things together, none of them is going to tell you your structure is definitely wrong or definitely right, but these are numbers that allow you to check the structure and get your own feeling on the structure. And that's all for the crystallographic refresher. I know it was quick, it was definitely not complete, but as I said at the beginning, it should give you some basis of say the basic knowledge, the basic concepts that are used in crystallography and in the solution of crystal structures. Thank you. Okay, so now we are offline. Hello. We'll continue the workshop with the second lecture with the title Jana 2006, an overview. This lecture will be quite different from the first one, and also different from the rest of the lectures in this workshop. It's not a tutorial lecture, it's more, as the title says, an overview of the program Jana 2006 that we will be using for this workshop in the practical sessions. You see the authors of the presentation are listed as myself, Václav Petříček, and Michal Dušek. In fact, if the list of authors should be ordered by order of importance in contributing to the program, then it should be Václav Petříček, Michal Dušek, and myself, because the main developer of the program is Dr. Petříček, who works on the program now already for more than 30 years. The program has been developed at the Institute of Physics in Prague. You see, this is a picture of the building, and the room of Václav Petříček is here, and that's where most of the now almost 1 million lines of code of Jana have been written and developed. Not all of that, but a large part. This is a picture that's a few years old, but actually we had a very similar situation last week. So a different scenery and different setup. So the history of Jana started in 1980s when Václav Petříček started writing the program SDS for the determination of ordinary 3D structures, and then during his stay in the United States, he developed another program for the refinement of modulated structures. So the main topic, or the raison d'être, the reason for being for the program Jana, is its ability to work with non-periodic structures, with modulated structures. A little word about the name Jana. So the pronunciation is not Jana, as would be natural for English speakers, but it's really Jana. That's the pronunciation in Czech, and it's actually a name of Václav's daughter. So he named the program after his daughter because he was homesick in the US. So he named his programs after his family members, and this name just stayed until now. So it's Jana. Then the history continued in 1996. There was a first graphical interface, and then there was actually a continuous development of the program, and these different versions are just labels for substantially new or modified versions. So the current version that we are using is called Jana 2006, but if you go to the web page and download the version, the latest version, it's rarely older than 1 week. So there is almost every day and every other day there is some modification, some bug fix, or an improvement. So it's really a continuously developed program, and then we are really preparing a major modification for this or next year, which will probably be called Jana 2020. So Jana is a program for structure analysis from diffraction data in the widest sense of that word. So it can work with X-ray diffraction data, neutron diffraction data, or electron diffraction data, and it uses powder data or single crystal. And they can be actually combined. So you can also do combined refinement of, for example, powder neutron diffraction data with single crystal electron data or single crystal X-ray data. So you can do combinations of data sets. So whatever data you have, you combine them, you import them in the Jana, in the program, and then you get a general data repository which contains all the data and allows you to continue with that. Then the general outline of the program is like this. So we import the data, that was the last screen, and then we have a collection of files with funny names. These names are M50, M40, M95, M90, and a couple more. These originated originally from a requirement of certain operating system to have extensions with M and a number. So at the beginning it looked like a nuisance, but actually nowadays it's an advantage, because like this, the Jana files do not interfere with other files in the system. If there were files like ins and struct and HKL, there are many different HKL files in the computer usually, and it would be difficult to distinguish which belong to Jana and which do not. So here all the Jana files, or the important Jana files, have the extension .m something, and you can be sure that this is the Jana job and no interference with anything else. So here you see the list of the most important files. So M95 contains reflections, M90 contains processed reflections, so for example with systematic absences excluded and with reflections averaged by symmetry. M50 is the crystal information, symmetry, unit cell dimensions, twinning, and so on. And M40 is the structure model. So we obtain the reflection, the processed reflection files from the raw data. We solve the structure and obtain the structure model in M40, and then we can do all the other steps: refinement of structure, transformations, interpretations, and so on. Jana is, as I said, very general in the type of data you can work with. So this is the first interface or first form that you face, and I will just very briefly go through the options just to show you what are the options. So you can import single crystal data, powder data. You can import also existing structure model, and there are specific options for magnetic structures. So either you measure the data with a diffractometer, and then you can import the diffractometer data, including all the metadata with the known unit cell and so on. Then you have all these types of diffractometers that are already predefined in Jana, and so there is a good chance that your diffractometer is in the list. If it's not, it's possible to just write an email, and if it's a reasonable request, if it's not one of a kind in the world that will never be used again, so if it's a reasonable request, it will be added in the list. Or if you do not have the data in any classical standard format, you can still import the reflection file, just HKL intensity sigma coming from any source you might have. So again, there are many different types of formats that you can import. If you have powder data, you can import various CW is constant wavelengths, and again a large list of possible powder diffraction data format that is predefined. And you can even, you have free format So you can import even data that do not correspond to any specific format, just specify the free format. And then you can import structure. So if you solve the structure using another system, typically Shellix, you can, and you feel that you need some special feature of Jana, you can import the structure from Shellix and continue working with it in Jana. So when I speak, speaking about features of Jana, you see here the list of features or topics I want to cover, and the first topic is basic crystallography, and this is all. This single line covers all the standard crystallography that other systems contain. So whatever you want to do for normal structure solution, data processing, structure refinement, modifying of the model, completing the model, and so on. That's all basic crystallography. And then we have advanced tools for standard structures. So even for standard structures, you may need some specials. And then there is a list of real specialties that make Jana so powerful. And these are modulated structures, so aperiodic structures described in superspace. We'll have a special lecture on that on the last day of the workshop. Composite structures, which are specific type of modulated structures. There are magnetic structures, a refinement of magnetic moment ordering within the crystal structures from neutron diffraction data, and also electron diffraction with a special feature of dynamical refinement, which allows you to solve and refine crystal structures from electron diffraction to accuracy comparable with X-ray diffraction data, but from very small crystals. So Jana is, in a certain sense, old-fashioned. It's written in Fortran, and it's using its own graphical library, so it doesn't look as slick and modern as the modern programs that are using the Windows-based graphical system. But the advantage is that it's very, very flexible, and it's not bound to the limitations of the operating system. There are a few things that are not included in Jana, and that is the phase problem solution. So the actual step of giving you the initial model from the diffraction data, but Jana can seamlessly bind with structure solution programs like SIR, like Expo, Shellix-T, and there is also one program that's delivered directly with Jana that's called Superflip. So you do not need any external program to start solving structures. Then Jana currently does not have a plotting option, so within Jana you cannot plot the structure. You need to call external plotting programs. That is currently probably the strongest limitation of the program for common user, but that is going to change in the version Jana 2020. And also there are certain validation and geometry analysis tools in Jana, but for really fine and final validation, we rely on Platon as most other crystallographers. So the Platon is the ultimate validation tool for standard crystal structures. Again, for modulated structures, that's something different. Okay, so for basic crystallography, Jana has a concept of wizards. So you have a wizard for data import. So you do not need to do it manually. You are guided through the process, offered options during the process. There are tools, graphical tools for editing structure parameters. There are tools for adding hydrogen atoms. If you need to decorate your structure with hydrogen atoms, there are tools for that. And then you can apply constraints, restraints. You can calculate Fourier maps, so electron density maps, and view that to validate the structure. And finally, you can generate a SIF from Jana to deposit with your structure, with your publication on the crystal structure. When you do the refinement, you can follow it on the screen. So you see the evolution of the figures of merit. This is the typical screen that it looks like, and you have the goodness of goodness of fit here, which is given by this formula, and it tells you somehow how well is the data described by the model. You may know that the ideal goodness of fit is 1. We should approach that value. And then there are various R values defined with standard formulas. And there is also a damping factor which allows you to damp a bit the refinement if it starts oscillating. So if there is certain instability, you may limit the shifts during the refinement to keep it more stable. The Fourier methods, very important, especially for more difficult structures. You need to check the electron density, the difference electron density, to see to look for any unexplained or wrongly explained features in the model. So there are many different types of Fourier maps that you can calculate. This one is an example of a difference Fourier map with wrongly assigned atoms. So this would be nitrogen, and you see there is a large difference, negative difference maximum under nitrogen, showing that should actually be less electrons, so you should replace the nitrogen with carbon. You can also directly call a 3D visualization of electron densities. We will do it frequently in the practical session. So this is a 3D visualization of the structure with these yellow isosurfaces showing the features in the difference electron density, and in this case these features show the missing hydrogen atoms in the structure. Very important feature in Jana are different types of transformations. So often it can happen that your initial guess for space group or even for unit cell parameters is not correct, and you need to transform to go to the subgroup or transform the cell, and this can be done very easily and in a very elegant way in Jana. And one reason why it is so easy and flexible in Jana is that Jana does not internally use any tables for space groups. Everything is done using linear algebra, so any setting of space group is possible, any group-subgroup relation is possible. There is nothing like a non-standard setting that Jana could not work with. So therefore also the transformations, the symmetry transformations are possible in a very general manner. Ideally, if you refine a structure, you would like to refine all atomic positions independently and really get the structure as independent of external information as possible. But sometimes this is simply not possible because the data do not contain enough information to give you, for example, the positions of hydrogen atoms completely. And you may need to impose certain types of constraints or restraints in the data. We will have a special lecture on constraints and restraints. So here I just very quickly say what's possible in Jana. So in Jana you can restrict, for example, the vibrational parameters, the displacement parameters of two atoms to be the same. Or you can also restrict the positions of two atoms to be the same. If you have a mixed site, you can say that these two atoms have the same position but different chemical element, and they are mixing together. You can also introduce symmetry relationships between atoms. If you have a molecule that has certain local symmetry, you can say that the molecule has a symmetry even though it is not a symmetry of the entire structure. So this is an example of the setting of restrictions. And this is saying that oxygen 2_1 is related by local symmetry 1 with oxygen 2_2. So that's an example of local symmetry, and it binds the coordinates, the modulation, if there is a modulation, and also the displacement parameters with this local symmetry. There is even more general option, and this is setting equations. So every parameter in Jana has its name, and you can set up a linear equation between any parameters in Jana. So this is an example of a very unusual, I would say even unreasonable equation. It relates the x coordinate of silicon 1 to some constant plus the y coordinate of silicon 3 minus 0.2 times the displacement parameter of oxygen 1. It's difficult to come up with a scenario where you wouldn't want to bind coordinates with the displacement parameter, but it just shows the flexibility you have in Jana with setting up equations. You can really bind equations or use any parameters you want, and again in one of the examples we will set up an equation that will ensure an overall charge balance in the whole structure. So you'll see how this is practically applied. Then there is a large family of keep commands which relates features of different atoms. So you have either the hydrogen keep commands. So the hydrogen atoms, they are so weak scatters that they rarely can be refined independently. So you can say that the hydrogens are related geometrically to the atoms they are bonded to. So there is very often a strict geometric relationship. And you can also specify their ADP parameters, or you can have a keep command on geometry. For example, you can fix a set of atoms to be planar. So these geometrical restraints, these are different types of geometrical restraints. If you have heavy disorder, you may need to describe the different disordered parts of the structure with rigid bodies. So you have one molecule and you place it in different positions in the structure, but these positions are not completely independent. They both contain or all contain the same molecule with the same shape. That is also possible using the rigid body concept and molecule concept in Jana. Potentially very powerful, in practice not so often needed, is the possibility to assign local symmetry to a molecule. This is a showcase example. This is a fullerene molecule which has its own very well preserved or defined icosahedral symmetry, and you can either define this molecule with 60 independent atoms which you would need to restrict somehow to hold the symmetry, or you can define it just with a single atom and saying this atom forms a molecule with this and that point group symmetry. So you can, in Jana, you can define the whole fullerene molecule with just a single atom and the local symmetry. This comes from a publication on powder data from fullerene. You can imagine that powder data contain not enough information to describe completely independently the atoms of the fullerene, but with this local symmetry, it reduces the number of parameters immensely. Another advanced feature that is useful for inorganic structures and especially for ionic conductors, where some atoms do not have very well defined position, but they may occupy channels in the structure and so on, is the so-called anharmonic displacement parameters. So that's the typical description of vibration of atom or uncertainty of position of atoms in the structure is the harmonic approximation. So the atoms are assumed to vibrate as free harmonic oscillators, so their shape is visualized as ellipsoid. But in some cases, in complicated environments, this may not be the right description of the atom, and the atom may be occupying a more complicated shape than just an ellipsoid. And then in Jana you can refine anharmonic, so beyond elliptical shape of atoms up to a tensor of 6th order. And then it allows you to describe even such complicated shapes of electron density quite accurately. This is a section through that, so it's a section through this shape. And here you can plot potential curves, and you can then discuss how easily the atom can move from one place to another. And then if you have ionic conductor, you may have a connected channel of these low potential path through the structure, and you can infer on the conductivity and ionic conductivity of that material. Yeah, so I mentioned the transformations. So this is an example of a group-subgroup transformation. So this is an example taken from a modulated structure, but it works equally well for a standard structure. So you have a space group, in this case C2 over M, with some addition specific to modulated structure, and you want to transform it to C2, which is a subgroup. You choose the corresponding symmetry elements, and then Jana constructs automatically all the rest. So changes the symmetry, introduces twin laws if necessary, twinning, transforms the unit cell to standard setting if by the transformation you obtain a non-standard setting, and so on. This is very useful for twinning, and we will have quite a few examples on twinning in this course. So you will see how the transformations or how this concept works. This is an example of a relatively complex twin. It's a threefold twin in a pseudohexagonal lattice symmetry, and we will work on this as one of the examples. Okay, I will very briefly go through other topics that are not so closely related to our workshop, but one additional option is the multiple refinement, which is a way to describe non-spherical electron diffraction effects due to bonding. So in normal structure description and normal structure refinement, we assume the atoms are spherically symmetric, and there is actually no physical interaction between the atoms. So there is no accumulation of electrons in covalent bonds, for example, or no depletion of valence electrons from cations to anions. But in reality, of course, these effects are there, and it's possible to take them into account using this concept of multiple refinement, which expands the electron density to this relatively complicated expression, but it just allows you to deform the electron density to non-spherical shape. And this is what you get out of that. This is a difference density on oxalic acid molecule. So atoms are here in these points, and here these red blobs or maxima, they show you the accumulation of electrons in the covalent bond between oxygen and carbon. In this case, these are the lone pairs on the oxygen. This is covalent bond between two carbon atoms, and so on. So you can describe really quantitatively the deformation bonding effects in the structure. It's common to have polyphasic samples in powder diffraction. Of course, in Jana you can work with powder diffraction with multiple phases in the powder diffraction pattern, refine them simultaneously, but you can have also multi-phase single crystals. If you have an oriented intergrowth of several phases in a single crystal, you obtain a single crystal pattern, but that contains more phases. That is also possible to treat in Jana. It's actually treated as an allotwin, so twin of two different phases. They can be both described and refined simultaneously. I told you at the beginning that the main highlight of Jana is its ability to refine modulated structures. We will not do that in this workshop, but we'll have a lecture on modulated structures on the last day of the workshop. But if you encounter modulated structures or want to know something more about it, of course I'll be more than happy to discuss that later or anytime you want. But Jana is nowadays, I can say, it's the only program that's really actively being used for the description of incommensurately and commensurately modulated structures. So that's it is the reference software for this for this kind of structures. So there are many things that you can do. There are many types of modulation functions that you can introduce, and even in this area, Jana is still being actively developed. So the last addition, for example, to the capacity of Jana is the possibility to define discontinuous modulation functions in two-dimensionally modulated structures, which has not been possible so far. Composite structures are a very specific type of structures which contain two substructures with different lattice parameters. And here you can see that we have the black spots which have the lattice spacing C1 in the vertical direction. So this is the unit cell of the black spots, and then there are the white spots, and they have the unit cell C2. And these two, C1 and C2, they are not a simple ratio. So the C2 is slightly more than 1/2 of C1. You can see. And such structures exist, and they can be also described as modulated structures in superspace, and Jana can do it. This is one example of a real structure. It's certain it's perovskite type. It's called hexagonal perovskite, but in fact it's a composite structure which contains these trigonal prism alternating with octahedra, and around that there are strontium cations which have a different periodicity along C than these octahedra and trigonal prisms. One of the last additions and quite important improvements in Jana is the capacity to refine magnetic structures. These are being refined from neutron diffraction data, usually powder diffraction data, but there are also, of course, also single crystal neutron data, and it's possible to refine magnetic structures, both periodic and non-periodic, so incommensurate magnetic modulations in Jana. So this is again an example of a magnetic structure, and these arrows here show the distribution of magnetic moments. In this case, this is a modulated structure where the magnetic moment oscillates between these two positions as a function of the position of the atom along C. So if you would see it from the side, this structure would see that the magnetic moment is doing something like this, so moving up and down. And finally, Jana can also work with electron diffraction and can do work with electron diffraction in two different, let's say, manners. One is to consider it as equivalent to X-ray diffraction, so treat it with the so-called kinematical approximation, and then it's really completely equivalent procedure, solve, refine structure, but the results are not so good because electron diffraction has certain specific features that are not present in X-ray diffraction, and these specific features, especially multiple diffraction that occurs in electron diffraction, these can be also treated in Jana. Oh, I see that. Oh, unfortunately, the movie is not running. This should be a movie showing the difference electron density on this structure. Never mind. So you can use this dynamical refinement in Jana to get really quite high accuracy results from electron diffraction on very small crystals. So if you have powder data, you can't extract single crystal from that. For electron diffraction, it's enough to have a crystal of the size of about 100 nanometers to get single crystal structure refined. Okay, with that we come to the outlook, to the not so distant future anymore. So the idea for the next version of Jana is that there should be an integrated structure viewer inside Jana, and all these features that are now available in Jana should be somehow accessible from the structure viewer. So you click an atom to change its parameters. You click a collection of atoms to change it to rigid body or to move it to a molecular part, and so on. So that should make the use of the program more user-friendly. than now when you need to call the external plotting program. There is a web page for Jana. The name of the web page is Jana.fzu.cz. FZU is the Institute of Physics domain, and there you find the version for download. You find also the so-called Jana cookbook. I'll speak about it in the next slide. And you find also the announcement of so-called ad hoc workshops on Jana. And these workshops are also a specialty of the Jana team, or say the concept of Jana. We organize workshops upon request. So if you are interested in a certain specific topic of Jana, because you've seen that there are many different things you can do in Jana, and it's not possible to organize a workshop that would cover everything. So if you are interested in a specific topic, you can sign in for that topic, and if there are enough people interested in the same type of topics, then we contact them and say, okay, we are organizing a workshop for you. And the minimum that we in general set is 5 people interested in the same collection of related topics. So if we get 5 people, we contact them, organize the workshop on that topic on a date that is suitable for them, and then we announce the workshop publicly, and there are other people who can join. The workshops are usually 2 days, and they are organized in Prague, so a bit far from here, I understand, but they are free. So the only thing that needs to be covered is the journey and the accommodation, which is reasonably accessible in Prague compared to other European cities, and the workshops as such are free. There is no documentation for Jana 2006, unfortunately, but there is a good reason, because there are so many features that it would really require many years of a person's full working load to write an exhaustive documentation, and because Jana is changing almost every week, this documentation will become obsolete the very same day it's written. Almost. So it's unfortunate that it doesn't exist, but at the same time I know that it will never exist. It's just not possible. But we have a replacement for the manual, which is called Jana Cookbook, and this cookbook is a collection of examples covering essentially all possible features that Jana can be used for. So we have single crystal data, powder data, standard structures, modulated structures, electron diffraction, magnetic structures, twinning, disorder, rigid bodies, everything is there. So if you have a specific problem, you just need to find an example that treats that problem, learn that example, do it, try to understand what is happening, and then apply the concept to your own data. We will use a few examples from the cookbook. We developed a few new examples that will be again introduced in the cookbook, so the cookbook after this workshop will again grow by a few examples. It has now already, I think, over 400 pages, and it keeps growing. So to conclude, as I said at the beginning, the main developer of Jana is Václav Petříček, and he's been really active over this for now almost 40 years, and he is still working on it almost every day. Michal Dušek is a second driving motor behind Jana, and there are many other people who contributed to the development of Jana, either by collaborating on different special features or by even just reporting bugs and suggesting improvements. Jana 2006 is being continuously supported by the Academy of Sciences, which we belong to, so we are paid by the Academy of Sciences, and we are also occasionally supported by projects by the Czech Science Foundation. Jana 2006 has always been and will always be freeware, so you can just go to the website and download it. You even do not need to register, but we appreciate if you register. we have at least certain rough idea of the number of users, and you also get information about important updates. So if you register, you get an email that the new version Jana 2020 has been released, for example. So the motor for the development of Jana are the users, the feedback of the users, the good feeling that we can contribute to other people's effort, and also if you use it, please cite it. And the citations are, these are the numbers that we report to our bosses to show that we are useful. I think that was it. Thank you. Okay.
I have one question.
Yes.
How many times? You have shown a couple of geometries, right?
Mm-hmm.
Bragg geometry.
Oh yes.
So in case we don't know the geometry, so can we use the unknown?
Yes. You can use the unknown geometry. There might be certain limitations on what you can do if you do not know the geometry. I'm not that much of an expert for powder diffraction, so I don't know the details. But you may have problems using the particle size